Good afternoon, everybody. Welcome to today's algebra seminar. And our speaker today is Victoria Lebed from University of Caen, Normandy, and she will tell us about the word problem for certain Hecke-Kiselman monoids. So please, Victoria.
Thank you very much, Walter. Thank you for this opportunity to speak in Uppsala, even if it is virtually. It's a great pleasure for me to speak at a place where some of the people who are the origin of the objects I will talk about come from. And thank you for teaching me how to pronounce Kiselman correctly. I'll do my best to do it well. So today I'll tell you kind of a personal story of a diagrammatic thinking person, myself, coming across some purely algebraic objects. And I will try to convince you that drawing pictures, colored pictures like the one you can see in the picture, can totally make sense in trying to understand how these algebraic objects behave. So let us start. In the first part of this talk, I will talk about one particular instance of the Hecke-Kiselman monoid. So it has n generators, and we impose three kinds of relations on these generators. First of all, we want all of them to be idempotent. Then we want the generators with not neighboring indices to commute. And finally, we would like to impose these kind of strange relations on neighboring generators. So all these relations are governed by some directed graph, which tells you that whenever two vertices are not connected, the corresponding generators should commute, and whenever they are connected, they should satisfy this kind of a triple relation. Note that it is not symmetric, so it's in the last part it's important to tell which one is before the other one, xi or xi plus 1, and the orientation of the corresponding h tells you who should be the first one. So this since this is governed by this linear graph, I personally call these monoids linear, Hecke-Kiselman monoids, or also monoids of type AN. But as you can easily imagine, you can define the same kind of object for any oriented or partially oriented graph. So in this first part of the talk, I'll try to tell you that to convince you that these objects are not as exotic as they might seem. I'll try to explain you where they come from and where they can be applied. And I will tell you that we know almost everything in a certain sense about these kinds of objects. So this part will contain essentially only known material, but I will try to be slow on this part in order to introduce all the tools I'm going to use. So the really new stuff comes in the second part of this talk, where I'll talk about the big brothers of these monoids I have just defined, the ones corresponding to one circle, to the circular graphs. So I will call them circular Hecke-Kiselman monoids, and they will be very similar. Just instead of one commuting relation, you will have one relation of the third type, because the vertices 1 and n now became neighboring because of this one additional arrow. So combinatorially, these monoids will be much more complicated than the linear ones, but I will try to show you that the kind of the pretty elementary tools from the first part will still be applicable and give really new results for these objects of the second type. So now let's try to think where this all these objects can come from. So the starting point will be the monoid of positive braids. By this I mean that we have n strands going from endpoints downstairs to endpoints upstairs, like the pictures you can see here. And I will read everything from bottom to top here. So these generators xi correspond just to one elementary crossing between the strand number I and strand number I plus 1. Then you have the n elementary crossings like this if you work with n plus 1 strands. That is where the generators come from. And in general, where people are more used to work with braid groups, where these crossings can be like this or the opposite side. But the objects I'm interested in here are positive braid monoids. And so in order to describe all braids, you just need two types of relations. You need this far commutativity, which is very easy to understand. It just means that if your indices are far away, then these crossings happen at different parts of your diagram. So the height of this, the relative height of these crossings can change. And the most important part of the relations is the second type relations, the braid relations. Here, I've just drawn them. In this monoid, multiplication corresponds to stacking one braid on top of the other from bottom to top. So here you have on the left you have x1, x2, and x3, and x1, sorry, and on the right you have x2, x1, x2. So these are precisely this equality, and this relation just means that you can take one strand, for example, this strand which is the closest to you, and you can push it to the bottom of the diagram so that it comes over the crossing. So this is a completely natural topological move, which is called the Reitmeister-3 move, and you can prove a theorem saying that these two relations is everything you need to describe to describe isotopy between two braids. So this is a very natural object which is studied a lot. Now, this object is rather difficult. For example, if you want to study representations of it, it's very, very difficult to describe all of them, or at least all of them if you impose some conditions. So a first natural step is to look at some quotients, some finite quotients. The most natural one is saying that, well, we can ask all generators to be involutive, and it gives you the definition of the symmetric group on an element. A slightly less familiar choice can be to impose every generator to be idempotent. This is what is called the zero Hecke monoids and comes under a bunch of different names. And more generally, you can take the algebra of this monoid and quotient it by some generic quadratic relation, which gives you what is called Hecke algebra, and which appears in many branches of mathematics. And regarding this idempotence relation corresponds precisely to one parameter in this quadratic relation to be equal to 0. This is why it's called zero Hecke monoid. Now, why are these quotients finite? The argument is very simple, but I prefer giving it just for you to have a feeling of what of how these topological considerations can be useful. So in the case A and B, in the involutive and idempotent case, the argument is similar. If you want to prove that the monoid with these two relations plus the idempotence or the involutive is finite, you need to do some Beigen keying. So I was too lazy to draw it properly, so it will be handwritten. I will explain it step by step. So first, if we have some minimal Beigen, on the level generators, it corresponds to having some xi followed by xi. So it is either identity if you're idempotent, if you're involutive, or it's just xi when you're idempotent. So you can reduce the number of crossings. As usual, when I draw diagrams, I mean that outside these diagrams, there can be very different things happening, but I'm just looking at some local picture. Now the second case is when you have this Beigen, which is not empty. It can be intersected by some other strands, which I have drawn in green, but there are no crossings inside this Beigen. In this case, the relation you had on the generators allows you to pull all these green strands up so that you are now left with a minimal beigen, and so you can proceed as you proceeded before in case 1. And in the general case, you take a beigen. We can suppose that there are no beigens inside it, because otherwise take the minimal one in this sense. Then since there are no beigens, if some strand enters this picture by one side, it should go out by another side. And if there are some intersections inside, there should be intersection between a pair of neighboring neighboring strands. Neighboring means that they will intersect the right side of your beigen in neighboring points. Because if all neighbors are pairwise non-intersecting, you will be in the situation which we have seen before. So let's suppose we have such kind of thing. Then once again, because you have no internal beigens, a strand can enter this triangle only by one of the green strands, and it can go out only by the other green strand, because we assume that on the right there is nothing, and you cannot cross the same strand twice. It means that you have a picture like this with some braiding, some intersection happening here inside. And you can take this upper green strand and pull it over this braid, because once again you have this topological radiometer 3 move. And then this green crossing, you can pull it to the right using the same topological move. And it means that you can reduce the number of crossings inside your beigen, and if you do it a sufficient number of times, you are in the case number 2, which has already been seen. So this is a rather elementary argument. What is important is that it can be translated completely into an algorithm, into an algebraic algorithm. It will be something very unpleasant to read, but it can be totally programmed by a machine, or it's a totally valid argument. But if you have this topological picture behind it, you understand perfectly what is going on and how to conceive such an algorithm. Why is the beigen killing interesting? If you have killed all the beigens, it means that you will have diagrams where every 2 strands can intersect only once. It means that you can have too many intersections, and that is why your object will be definitely finite. That is the proof. And now the last part of the defining relations remaining is the green one, and this comes from the work of Kiselman on convexity theory. He regarded the space of certain types of functions where he regarded three operators, and he was able to establish all the relations between these operators, and these were precisely these 3 types of relations. Later, Ganyushkin and Mazorchuk proposed to consider more than 3 operators and generalized these types of relations to a very general setting, going all the way through an arbitrary graph. So now I have explained to you where these relations come from, and we should know that these objects also appear in computer simulations. So the work of some Italian mathematicians. So the idea is again to start from a graph and to think that you can have some all these points can update the information on the points to which the arrows go. So the first object can update the state of the second object, the second of this third, and so on. And if you try to think all the relations between these information updates, you will come precisely to these kinds of relations. For example, if the object 1 updates the state of the second object twice, it's the same as doing it only once, because it is the same kind of information update. Or for for the third type of relations, if the first object updates the state of the second object, and the second object updates the state of the third object, then the first one can once again send some information to the second one. It will give nothing new. So this is all these relations can be understood in this type in this situation, and these guys prove that there are no other relations concerning these information updates. This is a very natural object, and I will just mention that these objects also appear when you are thinking about the representations of path algebras of quivers corresponding to the same graphs, and they come from projection functors, which were considered in a series of papers by Grensink and then Grensink-Mazorchuk. Now I will talk a little bit about the representations of these monoids. On the first hand, we'll see that there are a lot of representations, which means that the objects are not as exotic as they might seem. And on the other hand, I will define some representations which will be useful later to distinguish between different um, objects of my monoid. So in the general case, if I just write you two words and this generalizes, it's very difficult to say if they correspond to the same object. But these representations will be helpful in deciding that some objects are different. And so to understand, I will consider only representations of a very particular simple type, and they will be motivated by this topological picture. So if I say that downstairs we have n+1 points, they can I think that I'm thinking of them as corresponding to n+1 copies of the same set. And since I read everything from bottom to top, I see that something should happen to the copies of my set number I and I+1. So some operation should be applied, and I do nothing for the remaining ones. That is precisely the idea behind the following definition. I call an Allen chain on a set a collection of idempotent maps that satisfy this condition on A times A times A. This condition is just one of these relations defining the Hecke-Kiselman monoids, which is written down. And this definition is made for the following proposition to be true. The linear Hecke-Kiselman monoids will act on n copies of A by this relation. It means that you apply the corresponding sigma y to the copies of A which you find in the positions I and I+1. It is precisely the thing dictated by your diagram. When you take all these sigma i's to be the same operator, you recover the notion of the Yann-Bakst operator, which satisfies two additional conditions, this Kiselman condition and the idempotent condition. And there are plenty of very simple examples. First of all, as the maps, you can take the following one. You send A and B to A and py of B, where the p's is any collection of projectors. Very simple one. The second one, you can think of it as in the following way. You take the left component and you distribute it to the second one. So it is the same idea of this status update, but you can actually apply any fi here. So it's a very it's kind of general thing. And a particular case when I simply propagates to the right helps you to recover the Catalan monoids. So I will just explain it on an example. So whenever crossing happens, the left color propagates to the left and the right. It means that this color 1, it will propagate to 3 positions. This color 3 will go only here. The colors 4 and 2 disappear, and 5, nothing happens to 5. And this gives you a map which will be monotonous in the non-strict sense, and it will be decreasing in the non-strict sense. And these decreasing monotonous maps are precisely the elements of these Catalan monoids. And so this using this map and applying it to the data 1, 2, 3, 5, and up till n+1, you get precisely this bijection. Up. And one more type of these maps giving representations to A and B. You can associate it. You can associate one and f of I of A times B. So here, suppose that A has an additional monoid structure, and Fi is any monoid morphism, for example, the identity map, if you wish. And this example actually comes from this theory of Jan Baxter maps, and it plays a very important role in the study of Hochschild cohomology. It's also something natural. And the last one, to A and B, you can associate A and A times B, where times is an operation which should be associative and absorbing. You have this absorbing property. For example, you can take integers with the operation min or max. So we have a bunch of representations. Now, when I'm saying that I would like to understand a monoid, I'm thinking about three very basic questions. First, understanding the size, then solving the word problem for a monoid. It means that when I have two words in the generators, I would like to understand if they correspond to the same element or not. And something stronger, the normal form. If I give you a word, I would like to rewrite it to something, to a canonical representative. Certainly, every question resolves automatically the two previous ones. But I prefer presenting them in this order. Now, I will give the answers to these three questions in the case of linear Hecke-Kiselman monoids. So this theorem is, I would like to call it as folklore, because I think whenever you study anything which is counted by Catalan numbers, you're sure that somebody has already done it. So there are so many books on Catalan numbers that in some equivalent form you will definitely find it there. So these pieces of this theorem appear in different kind of works, but I put it together in a way which will be convenient for me for the second part. So the theorem says the following thing. There are explicit bijection between four kinds of things. I will start with the first two. The first one is the elements of my linear Hecke-Kiselman monoids, the things I would like to understand. The second object is something which I call a web. By a web, I mean a weakly entangled braid, WEB. That's why it's called, I call it web. So it means that I have these braid diagrams, which you have seen before on n+1 strands, only positive crossings, and I want them to be bigonless and triangle-less. So I don't want to see bigons. It means every two strands will intersect only once. And I don't want to see triangles, which means that you cannot have three strands which pairwise intersect. So these are very simple objects, and as usual in topology, you should say that you consider them up to something. Here I'm considering them up to isotopy, which can change the height of my crossings, but which cannot change the crossing scheme. So I consider the crossings as kind of welded together, if you wish. Now it's very difficult. It's very easy to go from B to A. Whenever you have such a braid, you just cut it in simple crossings, and we have seen that the simple crossings can be described using the braid monoid, positive braid monoid, and the Hecke-Kiselman monoids are just quotients thereof. So going from B to A is very easy. Going from A and B is the important thing, and I do it in a very simple way. I have explained to you how to kill bigons, and precisely the same argument explains you how to kill triangles. Just instead of this idempotence relation, you'll use the Kiselman relation, which is precisely saying that whenever you have a triangle of any type, you can replace it by something without triangles. And as I explained to you before, this graphical procedure can be turned into an algorithm, so you can get rid of all the bigons and triangles. But the problem is there is too many choice in what you're doing, and you are not sure at all that at the end you will come to the same web. And this is the question, which the thing I will explain at the end of this talk. So why this idea of bicon killing and triangle killing gives you something well defined. So this I will leave for the end of the talk. And as I said, all this can be turned into an algorithm, into something called rewriting procedure. So it can be dealt with the tools of rewriting if you prefer rewriting to as an approach. Now the third types of objects I'm looking at are completely combinatorial, and they can be understood in terms of Yann diagrams, if you prefer Yann diagrams. Here I will just explain everything in terms of sequences of integers. So you have two strictly increasing sequences of integers between 1 and n plus 1, and the first one is strictly smaller than the second one. By strictly smaller, I mean term by term comparison. So this is a very simple algebraic object, and the very good thing about it is that these things are very easy to compare. I give you just two sequences, you compare them terms by terms. So the braids was slightly more difficult to compare because you had some choice, because you could change the height of certain crossings. And this object from C is completely combinatorial, completely easy to stock, to compare, and to do whatever you want to do. Now, how can we go from a braid diagram to this sequence? So I didn't mention it, but since I'm working only with positive crossings, I just forget the under-over information. I just draw the solid crossings for simplicity. To do it, you need to first show the following lemma. You should show that whenever you have a web, so a braid without bigons or triangles, you can isotop it to have something where all the strands will go either to the right, like the red ones here, or to the left, like the blue ones here, or strictly upwards, like the black one here. So this is a little topological lemma you need to show. And once you showed it, you can look only at the right strands and just write down the numbers of the lower endpoints and then the positions of the higher endpoints. And it will give you two strictly increasing sequences. The first one will be strictly smaller than the second one, and they will correspond precisely to the relations I wanted. And if you want to go from the other way, if you have this kind of sequences, you can just take n plus 1 points downstairs, n plus 1 points upstairs, mark the points corresponding to the numbers you have in your sequences, then draw segments relating them, and you can show rather easily. Then you can also relate the remaining points in a unique way, such that they will go strictly left or up. And it's relatively easy to show that these two things are well defined and they will be the inverse of each other. So here, as I explained, the objects from C are much easier to work with, but the objects of B are important to understand why we are looking at such strange kinds of sequences and why we are doing what we are doing with them. So for practical reasons, you will need almost everywhere the object of type C, but the objects of B are important for conceptual understanding of what is going on. And the last type of combinatorial objects I will going to look at are permutations. So if you just consider your braid diagram as a permutation, just see, you need just to look what vertex is connected with what other vertex. It gives you a permutation of n plus 1 elements. And if you have no triangles, it will be what is called 3 to 1 avoiding. 3 to 1 avoiding, it means that you cannot have 3 increasing elements downstairs, which upstairs will become decreasing. So you cannot have a pattern of in your permutation. You cannot choose 3 numbers which will make a decreasing sequence. Such avoiding pattern avoiding permutation is something which is looked at a lot by people from computer science. So it's a very wide and active area. And it's relatively easy to show that B and D are equivalent by the same kinds of argument that show that B and C were equivalent. And so what do we have now? We have these topological objects B, these combinatorial objects C and D, and we have seen more or less how to show that they're equivalent. We have seen that starting from a braid, you have an element of the Hecke-Kiselman monoid, and going the other way around, it was not easy. It was not clear that our procedure gives a unique result. And to do it, we actually need to regard the representation we have already talked about, the one which, whenever we have a crossing, propagates an element to the right. It will be the same kind of thing which I used to show that this thing is equivalent to the Catalan monoid. So if you apply your representation, if you look at what numbers survive upstairs, you will precisely understand what is these, what are the corresponding increasing couples, which means that, and since B and C are equivalent, it shows you that your map from A and B was well defined. So any web you obtain by Bagan and triangle killing will look the same, because if you apply this representation to it, it will have the same colors upstairs. This theorem gives you the answer to the 3 questions which were looked at before. So first of all, it gives you the size of these monoids. These are the Catalan numbers. For example, it's rather classical that the objects of type D or C are counted by Catalan numbers. It is less classical that these braid diagrams, these webs, are also counted by the Catalan numbers. So it gives you a kind of a new exotic realization of the Catalan numbers, which is rather interesting. Now, it gives you also a very easy solution to the what problem, which is linear. By linear, I mean linear in the number of letters used to write a word of your Hecke-Kiselman monoid. How is it realized? It's, well, you take a word in your generators and you make it act on n plus 1 elements, which are 1, 2, 3, and so on until n plus 1. So when each element acted, you look at the colors upstairs, and from these colors you easily read, let's say, this increasing couples of increasing integer sequences. So all this is linear, so it's a very easy linear algorithm. And you also have a normal form which can be computed in a quadratic way. There are 2 ways of doing it. First of all, well, from a word in the generators, you can construct your 2 integer sequences. Then, as I showed, from these integer sequences, you can construct a braid. It is very easy to do in a combinatorial way, and you just need to keep track of the you take your segments going from bottom to top one by one, you compute their intersections, and you order them by their height. And then you go through the list of your intersections and just write the corresponding generator. This will be a normal form. The only place where you will have choice is when two intersections will, two or more intersections occur at the same height. But you can make some choice saying that, for example, you need to write them from left to right. This is the only place where you need to make some choice. And another realization of this algorithm is the following one. From your couples of integer sequences, you can have your permutation, and then from this permutation you can write a word using some inductive process. Whenever you have two in your permutation two elements which whose order is inversed, you can say that this corresponds to the last letter of your word, and like this you reduce the number of letters, and this is also quite an easy inductive procedure. And probably in practice the second choice is easier, so it doesn't make any braid diagrams appear, but to understand what was behind this, it was rather crucial to look at braid diagrams. So now, in the second part of this talk, we'll talk about the circular Hecke-Kiselman monoids. So they look really similar to what we have seen before. There's just one thing changes. So on the level of the graph, we just connected the vertex number n with the vertex number 1, which means that the generators x1 and xn are now connected, and for them we'll have the braided and Kiselman type relations. So here the indices will go until n plus 1. So in red I try to show the changes. And we remove this couple of vertices from the list of commuting generators. So that looks very easy. This is a very important example actually, because certain types of questions, for example, the question whether the algebra of this monoid will be Noetherian, will have the Noetherian property, can be reduced to these types of monoids. So that's why I call it the big brother, the important thing. And let us look at what we know, what was known previously about them. So these monoids are infinite. I know of at least two solutions to the word problem for these monoids, which are actually equivalent. So one was suggested by Metzel and Agnieszki. It consisted of in looking at some explicit finite Grobner basis. And the other one was given in terms of confluent writing and confluent reductions, but actually if you look in detail they are doing precisely the same thing. The second one is due to Aragona and Andrea. And later Agnieszki with Wirtel continued this work on this finite Grobner basis and showed that from this it is possible to deduce the normal form of almost all elements. By almost all here we mean that all elements except for probably a finite number of elements. And their normal form is actually very complicated. So the proof of the fact that it's normal is a collection of rather heavy technical algebraic lemmas. But this was sufficient for them to prove this important Noetherian property. So they showed that if you take a field and construct the monoid algebra of this circular Hecke-Kiselman monoid, then you'll have a Noetherian algebra. And starting from this, they classified all the graphs for which the corresponding Hecke-Kiselman monoids give Noetherian monoid algebras. Now, the point of my work was to give a simpler, more complete, and more tractable solution to both word problem and this normal form problem. And the spirit of it is very close to what we did for the linear case. Once again, you can look at the representations which correspond to taking here n copies of some set, and then the corresponding generator xi will act on the copy number I and I plus 1 by some operator sigma I, and they should satisfy this compatibility condition, certainly. Well, if you want to write things down properly, it will be more difficult to write where this last generator xn comes from. You'll need to use a permutation, which moves the last component to the beginning. But this comes just from the fact that we are writing things in a line. So if we were able to write this n copies of A in a circle, we would not be needing this permutation. This means just apply sigma n to the copies of A situated at the position number n and at the first position. So if you imagine your words going in circle, this is something very intuitive. And all the types of representations which I gave in the linear case still work here. And the most important one which we'll need is again propagating A to the right with some deformation applied to A eventually. An example comes from the work of Aragon and Andrea. Again, A propagates to the right, and when when it is propagated from the last position to the first one, something happens to A. We apply some 1. It is to keep track of this circular condition. And I will return to this representation once more at the end of the talk. But just to keep in mind that we have a bunch of very easily constructible representations. So now we'll have a really similar type of theorem for the elements of circular Hecke-Kiselman monoids. Let us first look at the diagrammatic object we need. So we'll still call them n webs for weakly entangled braids, but we'll add a tilde to n because in the language in one of the possible languages this circular thing corresponds to the a tilde types. So what are these objects? They are still braids on n strands, but instead of drawing them on the plane, we'll draw them on the cylinder. Since it's difficult for me to make pictures on the cylinder, I will draw them in the flat way, but I will also always consider that the left part of my picture is glued to the right part of my picture. This gives me braids on a cylinder. Again, I consider only positive braids, so I'm drawing the flat type of intersections, not caring who goes over, who goes under. And I need 2 conditions on these braids. The first one is similar to the one we had. I don't want to see bigons and triangles, but here you should be more careful because on a cylinder you can have 2 types of bigons and triangles. The first ones are contractible. It means, for example, that if you draw your picture on the cylinder and cut them, well, you cut away just one piece of paper. So these are the examples. Here again, there can be any amount of strands doing whatever you wish. In this picture, there are only the relative position of these 2 or these 3 strands, which is important for me. Just to give you a flavor of what it means to be contractible, let's look at a non-contractible picture. So here you have, for example, 2 strands which intersect once, and then one of the strands goes behind it, makes a circle around your cylinder, goes back and intersects one more time this second strand. If you try to make this picture on the cylinder and cut it, you'll just cut your cylinder in 2. You will not have a small piece of contractible thing cut from it. You'll just cut your cylinder into 2. And here on the right, you have a similar thing. You can here I drew 3 strands. they make two triangles. Here you have a small triangle which is contractible, but if you look at the red lines, you have a non-contractible cylinder. And once again, if you cut along these lines, you'll just cut your cylinder into two parts. So the non-contractible cylinders are the non-contractible triangles and bigons are possible, but the contractible ones are not permitted. Now, the second thing, we want all our diagrams to be compositions of the elementary diagrams. What does it mean in practice? So here on the left, you have a picture which can be seen as a composition of elementary braids. So here you have D1, D3, then D2, D4. But on the right, you have still a braid which doesn't have any bigons or triangles, but it is not, as can be easily seen, as not a composition of elementary ones because you just don't have any crossings at all. This is a very important braid. It is called T, the Ttiprate, and it's important because you can prove the following thing. You can take any braid diagram on the cylinder, and it will be up to isotopy, a composition of some elementary ones and some copies of this T map. So altogether, they generate either the braid monoid if you're working with the monoids, or the braid group on the cylinder. And so we are looking only at a part of the braid monoid on the cylinder, the part generated by the elementary ones. And it's pretty clear why I need it. I need to construct a map from B to A. So I need to interpret all the pictures, and this picture I cannot interpret, and it's not interesting for me. And so you see very well how to go from B to A. Let us now try to understand how to go from A to B. And it's again the same story. You look at contractible bigons and triangles, and you need to kill them. And you have a very similar procedure to what we had in the linear case. And once again, you have a problem. You're not sure that different killing schemes always reside in the same web. Maybe they will give two different diagrams. And once again, I will show that they do give the same web at the end of the description of this theorem. Here, I'll just note that once again, everything can be reformulated as an algorithm or as a writing procedure. So everything is very explicit. Now, what is the combinatorial object we'll look at? This is, once again, we'll have couples of integer sequences. The first one is work in the same way we had before, just an increasing sequence of integers from 1 to n. The second one will still be increasing and bigger than the first one, but the relation on this second integer sequence is a circular relation. The last term cannot be bigger than the first term plus n. This is what I call n-close. N-close, increasing couples of increasing integer sequences. This is kind of strange object. It is not longer a Yann diagram, so it's something more complicated, but at least they are very easy to compare. So if you want a solution to the what problem, it's perfect. You just you get two sequences of integers, you can compare them term by term, and that's it. Oh, this is easy. And from this, you immediately see that your object will be infinite. So because you don't have any, the B1 can be as big as you wish. Now, how can we construct this type of thing, and where do these circular relations come from? The idea is this, as before, follow this right strands, but I will try to be more explicit about the right strands. So you can prove a topological proposition, which gives you the following thing. If we take a diagram on n strands, which is a composition of elementary diagrams on the cylinder, the following three conditions are equivalent. First of all, you can ask to have no contractible bigons or no contractible triangles. Then you can also ask no minimal contractible bigons or no minimal contractible triangles. By minimal, I mean empty. just empty. And the interesting part is the third part for us. Up to isotopy, you can isotope your diagram a little bit and make each strand either going to the right. To the right, it means it just goes to the clockwise way around your cylinder. Or you can go completely to the left, or you can be vertical. So each strand is of one of the third types. For simplicity, all the right strands will be depicted in different tones of red, and all the left strands in different tones of blue. So this will be my convention. And the difficulty with the braids on the cylinder is that it is not sufficient to know only where you start from and where you arrive to, because in between the two, you can go around the core of your cylinder as many times as you wish. This is what I call winding. So to understand these pictures, you need to understand the permutation, understand where each strand arrives to, and how many times it goes around the core, have this winding information. And a nice way of writing compactly the two pieces of information is the following thing. So if you go from A to B and you go around the cylinder W times, W from winding, so you say that A goes to B plus W times N. So since B is between 1 and N, it is a really compact way of writing the two numbers. So, and now if for each right strand you make this procedure, you'll arrive at two couples of sequences. We can look at an example. So here you have a strand on a braid on 4 strands. The fifth point corresponds to the first one. They just glued together. Now here you see that there are only two strands going right, the rose one and the red one. So the rose one goes from position 2 to position 2, the red one from position 3 to position 1. To count the twists, the easiest way is just to draw a straight line between 4 and 1, the green one here, and you just count the number of times you intersect these green lines. It gives you the number of twists around the core of the cylinder. So for the red one, you'll have for the rose one, you'll have only one intersection. For the red one, you have two intersections. And then you apply the formula. 2 plus 1 times 4 is 6. 1 plus 2 times 4 is 9. So you have two numbers. And so you have your two sequences. Each one will contain two numbers because you have only two right strands. This is how it works. And if you want to go in the opposite direction, you need to decode. And to decode this, you need just Euclidean division. So it's pretty elementary. Then, so if you have these two sequences of numbers, so first all the BIs, you decode them to get the permutation and divided numbers. Then you can draw these right strands. You know how many times you need to go around the core, and you know where you need to arrive. The easiest way to draw things are on the universal curve of the cylinder, which I will draw in the next slide. And then once again, you complete this by the left strand and the vertical strand. And once again, you'll have a lot of choice of where to go if you are going left because of these winding numbers. And the thing you will be using is that the total right winding number is the same thing as the total left winding number. And this is true because your diagrams are compositions of the elementary ones. So if you allow this T, this shift T, this will no longer be true, but without the shift T, this is true. So how does it look at an example? So we start with the example, with the previous example, we try to deconstruct. So we suppose that we have two sequences, two smaller than 3 and 6 smaller than 9. We apply the Euclidean division. The only thing is that instead of elements of having these remainders 0, 1, 2, 3, we have 1, 2, 3, or 4. So it is a very slightly modified version of the Euclidean division. So here we have 6, which mean that we'll have to get to the position 2 and make one twist. So here I drew the universal curve of your cylinder, which means that you cut your cylinder and you make a square, and you glue an infinite amount of squares on the right and on the left. And this, to go back to the cylinder, you need to enroll each square around the cylinder. So here you have the for the rows strand, you need the winding number 1, which means that you need to go to the neighboring square to the right. For the right one, you have 9. 9 is 1 plus 2 times 4. It means that you need to go to the second square on the right. And you draw your straight lines. Then you need the remaining segments, so the blue and the black ones. So here you see that the position number 2 and 1 are taken. So the remaining ones will be number 3 and 4. But to understand in which copy of the cylinder you will be living, you'll have this sum of twists, which can be translated as the sum of indices. So here the sum of the 4 numbers is 10. It means that upstairs you need 10 as well. And the neighboring numbers which give 3 and 4 modular 4, and which sum up with 6 and 9 to be 10 are minus 4 and minus 1. So it's an elementary computation. It means that you need to draw the lines like this. And then the only remaining thing is to go from this universal curve of your cylinder to the cylinder itself. So just enroll your picture around the cylinder. So here you need this enrolling, and it gives you this picture. And to get the element from your Hecke-Kiselman monoid, you just need to read this from bottom to top, and I write my elements from right to left. It's not very convenient, but it's convenient when you're thinking about representations, because you act from right to left. So here at the bottom, first you have a crossing between the third and the fourth strands, x3, and then between the fourth and the first one, x4, then x2 again, x3, x1, x2, x4, x1, x3, x4. So it's something very easy to write down explicitly. And once again, all this can be turned into an algorithm. You just compute where the intersections of these segments should be situated, then order everything according to the height of the intersection, and then just read them from bottom to top. So these two procedures, coding and decoding, can be seen to be the inverse of one another, which shows you that these webs on the cylinder are the same thing as the enclosed increasing couples of increasing integer sequences. The only remaining thing is to go from the elements of your monoid to the webs, or to the equivalent to the integer sequences. And here, once again, we'll use the representation, which is similar to the one used in the linear case. So every element should be propagated to the right. But here we have a slight change. When you're going to the last, from the last position to the first one, you add n. Adding n is much better than adding 1, because once again, due to the Euclidean division, you encode all the information without any loss of information. We can look at it as at an example. We take a word, which is the word we obtained from the previous example. You apply your map to it. So here, for example, applying x3 means that the 3 from the position 3 is propagated to the right. Then apply x4 means that the 3 from the last position propagates to the first position. But since we go to the first position, there is some n which should be added. Here n equals 4. It means that instead of writing 3 at the first position, we write 7. Then 2 propagates, and so on and so forth, and you get 4 numbers at the end. What does it correspond to? First of all, we look at these numbers modular 4. We get 3, 2, 3, 3. It means that the strand 2 should arrive to the position 2. The strand 3, well, it polluted some numbers, but if you look at the circular order, the rightmost position will be the first one, so it arrives to 1. And to get this twist or these winding numbers, you need to look at the corresponding numbers. So the corresponding number to the 2 will be 6, and to 3 will be 11. 6 is 2 plus 1 times 4. It means that there was 1 winding in the story. 11 is 3 plus 2 times 4. It means that the winding number is 2. And it means that here the position 2 you arrived to should be slightly modified to take the winding number into account. You need to add 4 one time, and the 1 here you should add this number n, so 4, 2 times, because the winding number is 2. And you get the number 6 and 9, which is precisely the sequence we wanted. So in the example, we have seen that all these three things, the word, the braid, and the sequence, they can be easily reconstructed one from another. The only thing we should mention is that here there is no natural interpretation in terms of permutations. So in the case of linear Hecke-Kiselman monoids, we had the interpretation in terms of 3 to 1, avoiding permutations. Here there is, at least I was not able to find anything natural in the world of permutations to complete this picture. But this is everything actually we needed, because well, we have seen that the size of this monoid is infinite. We have the what problem. This algorithm of constructing the couples of sequences gives you a very easy linear solution once again. And you can construct a quadratic normal form from this integer, because from these integer sequences you can reconstruct an element either by drawing the diagrams on this universal curve of your cylinder, which I showed you, or by creating an inductive process, which is relatively easy to write down. These are equivalent in complexity. So this normal form is much more readable than the normal form which was known before. It's easier to construct, and it has the advantage of being a total normal form, which means that it works for all the elements of a monoid without exception. And once again, if you take the second option, it means that you can do everything without ever mentioning the diagrams. But if you it will be something completely unreadable. If you want to understand what all these manipulations of Euclidean divisions and everything corresponded to, it's really helpful to think in terms of braid diagrams. Now, there are two very natural questions to ask. The first one, can this work for more general graphs? I don't think so, for a very simple reason. In general, there are no satisfying diagrammatic interpretations for, let's say, for Artin-Tits groups of type other than A. For type B, you can do something, but going to other types, it's not known. No reasonable diagrammatic interpretation is known. But even if you remain in type A, It means even if you have these linear graphs, the simplest ones, but if you orient them differently, you can have rather curious phenomena. So let us look at this example. We have three generators, which are all again idempotent. The first one and the last one commute, and you have braided relations between the first and the second, and the second and the third. But the Kiselman type relations go in a different direction because the two arrows are oriented differently. So here you have number 2, the second generator before the first one, and here the second generator before the last one. And you can look at these two webs. So these are clearly webs. You don't have any biangles or triangles. They're clearly not equivalent because, for example, the corresponding permutations are different. But if you look at the words which they represent, so let us look here. We need to read the diagrams from bottom to top and to write them from right to left. So here you have just some freedom in the choice of ordering them. Let's write 3x3, x1, x2 here. And here you have x2, x3, x1, x2. And so these words, they will be equivalent words in the Hecke-Kiselman monoid corresponding to this graph. And here I wrote how to go from the left word to the right word. And in red, I show the place where I apply a relation. So here for x2, x1, I have this Kiselman type relation. It becomes x2, x1, x2. Then for x2, x3, x2, I need another Kiselman type relation to write it as x2, x3. And then x2, x1, x3, I write it as x2, x1. So it's a proof that the two words are equivalent, but clearly the verbs are not. So you can prove that in this particular example, this is the only problem which occurs. So this is if you fix only this problem, then you will have precisely the equivalence of the 4 types of objects. You just need to quotient out the diagrams by this relation. This is the only problem. But if you consider something longer, some very strange phenomena comes to the picture. So this looking at webs is not, at least such as I presented them, is not necessarily the appropriate way of working with the generically oriented chains. But so of course I would be happy to find some other combinatorial flavored way of working with some more general instances of the Hecke-Kiselman monoids. So once again, I finished much earlier than expected, but I think it's not a problem. I hope so.
Absolutely. Thank you very much. Thanks a lot for very interesting.
Thank you for listening.
Are there any questions? I have a couple of questions. First of all, so when you look at this case with a cycle, is n greater than 2? So your basic setup for the second half for a n tilde. Because
no, I don't.
So how you define monoid if n is equal to 1 or 2?
Well, for n equals to 2,
you have two arrows in different directions somehow.
Yeah, I see what you mean. I was thinking, certainly in my head, you always have something bigger, but
yeah, you just had the picture of the cycle. Sorry, you jumped over.
No, I'm just thinking about the elementary diagrams. It means that you have 2 elementary diagrams which have, you can always impose this. Yeah, I see what you mean. You just
No. I mean, if you go to the picture of the cycle, which you have.
Yeah, I understand what you mean.
Yes. So if you have 2 points, you have 2 arrows between them, and somehow.
I think it's safer to say that n starts with 3 because otherwise you just have a commutative. Thank you for the point.
And the second thing, there is a notion. So for the usual Catalan case where you have just an uniformly oriented AN, so Catalan numbers are in bijection with Dick passes. And there is a notion of cylindric Dick passes. Is it relevant for?
I don't know it. I know the Dick passes, but I don't know cylindric Dick passes.
I'm not an expert in that notion, but I saw it in the literature, so I wondered
I
whether
should have a look.
Any kind of relevant.
I've never come across it. Thank you for the point.
And what happens if you look at this picture, which we now have the cycle, and instead of one oriented arrow, we just write an unoriented arrow. So we just remove the Kiselman addition of the corresponding braid relation. This becomes, of course, much more complicated, I would say, but.
So you want to do it for all the arrows or for one arrow?
No, only for one. Just to make it a little bit more complicated.
Well, it means that you are not able to kill all the triangles.
Yes.
So the whole reconstructing points will be quite difficult. I mean that you need much more information than just to understand what every single straight does. You need some interaction between the strands, and I don't really.
Maybe it's very difficult. I don't.
I've never thought about it. I was more interested in trying to reverse the orientation. But if you just remove it completely, it's a reasonable question because we know quite a lot about the braid monoids. So it's kind of unique between the two.
It sounds as this is the easiest case which doesn't fit into your result. It's the easiest generalization. So it's
a very good question. Yeah, I need to think about it.
Okay, but anyways, thank you very much. This is very interesting.